Thank you so much for the organizers, and I'm very happy to give the last talk of this conference. So today, in this talk, I propose a growth term having a discontinuity and show you some interesting consequence on traveling wave. So let us start with the familiar logistic growth. So if we consider the total population and its growth, if it is governed by intrinsic growth and self-competition, then we can model the growth of the total population by U sub t is equal to U minus U squared. So here U means intrinsic growth and this is self-competition. So we have the familiar logistic growth. Then we know that for any positive initial value, this is the solution converges to 1. Its state state is equal to 1, and any positive initial value converges to 1. But we know that, as Professor Alfaro has very interesting consequences. So it is reported that there is a situation where the total population U becomes extinct, goes to 0 if it is smaller than a certain critical value U star. So this is called the strong LA effect. Right? So to include such an effect, on one way, a typical way, is to multiply U minus U star to the logistic growth. So we have this growth term, which is called bistable nonlinearity. Then now we can see that if the initial data is less than the critical value U star, the total population becomes extinct, so the L effect is obtained. So this is one of the typical way to include L effect. So in this case, but this is just convergence to 0, and it becomes never 0, as we know. So it takes infinitely long time to become extinct, and the right-hand side becomes changed as a cubic decay, a cubic term, right? So the lowest term is quadratic polynomial, but this is cubic polynomial. So we ask, is there a way to avoid these 2 points? So for example, can you make this growth term to have a finite time extinction, or can you find a quadratic equation? So here in this talk, so we propose a new growth term by adding a constantly decaying rate minus epsilon. Okay, then we have this growth term, but obviously, if the population is 0, then it cannot become 0. It cannot become negative, right? Population is always non-negative. So the right-hand side should be 0 if U becomes 0. So we cut off this right-hand side by characteristic function of U equal positive. So this is a typical example of growth term we propose, and let us call psi of U here. Yes.
That takes 0 and U equals 1. Is that correct?
Okay. Sorry. I'm very sorry. So yeah. Okay. So that's my mistake. So its value itself is not important, but I'd like to show its shape here, and I choose this one, U and U star here. Okay. sorry. So the quantity itself can be changed. So I just fix one, but it is not necessary. Okay. So what did we do? Consider the logistic growth term. Then if we lower the logistic growth a little bit, then the graph looks like this, and just cut off where the U is negative part. And then we have psi looks like this one. So this part is just quadratic equation, quadratic polynomial, but at U equals 0, just psi equal to 0 and just 0. So, okay, so when U equals negative, it is not totally not important because U never becomes negative. But here, importance is when U equals 0, there is a discontinuity. So it is essential. So quadratic, and we have discontinuity at 0. Okay, then in this setting, we would like to find a traveling wave of this reaction diffusion equation with such a reaction term having a discontinuity. So X is the whole domain R, and we consider a traveling profile V and its traveling speed C. Okay, then, and also we assume that the integration of psi from 0 to 2, 1 here is positive. So this is a usual condition on classical traveling waves for traveling waves to have a positive traveling speed. So I just assume the traveling wave comes from the left and goes to the right. So it's okay to assume this one. So this part is big and this part is small. So I assume. Okay, then my claim is that we can find the traveling wave, and it is unique in some sense, and the traveling wave does not have a tail. So the traveling profile V looks like this graph, and it comes from 1, and it connects 1 to 0. It looks like this one, and this one constantly 0. So from the traveling front, the value of V is constantly 0. So there is no tail at all. And furthermore, the graph itself has a C1 alpha regularity. So at the traveling front, it is in fact differentiable. So, but also away from this traveling front, the solution is C2 alpha. So it is in some sense classical, almost classical. So from this picture, you might recall, if you well know of the Poisson medium equation, then there is a similar situation. Poisson equation can have compactly supported solution, but that is induced by the degeneracy of diffusion equation. But interestingly, this kind of no-tail behavior is just obtained by the reaction term. So this one interesting point. So how to prove it? Because our psi has a discontinuity at 0. So classical arguments such as a shooting method is not working. It is. I think it seems not so good to work with some kind of continuity argument. So instead of that, I will approximate this one as this graph by adjoining this curve to 0 curve, and this one we can assume this one is C1, and so if this part is C1, we can assume the total part is C1, and it is exactly looks like the usual bistable nonlinearity. So here we have discontinuity, but we eliminate the discontinuity, and we obtain the classical sense reaction term. Then with this approximate sequence psi n, this psi n approximates this psi in some sense. So this psi n is just a bistable nonlinearity, so we can use the classical theory. Okay. Let me go further. Then corresponding psi n, we can find corresponding traveling profile Vn. So Vn satisfies this kind of ODE is well known. And also we impose the boundary conditions because we'd like to connect from 1. So left part is just 1 and the right part is 0. So this is natural, and also its derivative vanishes. So it's classical. There is a classical solution Vn, and its traveling speed, positive traveling speed exists, and it's also unique up to translation. Right? So if we assume the point at the origin Vn has a certain value, for example, let us say U star. So this U star is this one. For convenience, I just set this one, U star. If we assume Vn satisfies this relation, then such a Vn is unique. So we have find a set of traveling waves, uniquely determined set of traveling waves. Okay. Then let us give you a sketch of proof. So main idea is from the sequence of traveling waves Vn, we can find the traveling wave we want. So for example, by Schauder theory, we can estimate a C1 alpha norm in a compact set of Vn by this quantity, and which is bounded by, so Vn is bounded by just 1. And this psi n is also bounded by psi u. So we have the bound of C1 alpha norm, Helder norm. So taking a subsequence, we can find the C1 alpha solution V for any alpha less than 1. So this V also exists in whole domain. We can easily deduce that for argument, because this convergence is all for the compact set, but because this Vn has a decreasing property, we can construct from this one whole solution, a solution in the whole space V, so which is in this space. So this V is what I want. That's what I claim. So to prove such a V is a traveling wave, we need to prove following 5 items. So let me just mention it. First, we need to confirm that such a traveling wave has a positive traveling speed. Okay, then to do that, we show that its subsequence Cn is bounded, and also it has a positive lower bound. Also, we need to show that with a weak solution in some sense. I mean, weak is usually weak sense, so it's easy. And also, we need to show V has no tail. And before I mentioned that V is a C2 alpha has a regularity, so we need to show it. So, but it's also from the Schauder theory. Yeah. So let me skip it. And finally, we need to prove such a weak solution is unique. But this uniqueness proof is almost similar to the classical uniqueness proof for the traveling waves. So I skip it. So let me say some more details for first item and third item. I think they can be interesting to look into it. So first we need to show traveling speed exists. So from the original equation, if we multiply Vn prime and integrate from minus infinity to infinite, then we have this equation. And the first equation, and the first term vanishes because the boundary term Vn prime is equal to 0. It vanishes, and this term comes to here. And finally, this one, if you look into this one, because Vn is decreasing, so we can transform this term as this one. So we don't need Vn here anymore. And we have just psi n, but as we know, psi n is an approximation of psi, so the right-hand side is okay, bounded, I mean. So this equation implies that to estimate C1, it suffices to estimate the gradient of Vn. Okay, so we'll estimate this Vn prime. But to estimate Vn prime, and now we use the classical energy for the traveling wave. So which is given by this one. So classical energy consists of Vn prime squared plus integral of psi n. Okay, then its derivative with respect to x is strictly decreasing. So energy at some point is bounded by energy at minus infinity and energy at infinity. So energy has a certain bound. So which in turn means Vn prime squared has a certain bound. So this is another. So this is a starting point to estimate Vn prime. So we need some more arguments, but let me skip it. So this is a good start point to estimate Vn prime, and then we have the bound for traveling speeds. So that's the proof of existence of traveling speed. Now finally, we need to prove there is no tail, as I claimed. Also from the original equation, if we integrate it from minus infinity to 0, then we have this one. So psi n here and integrate this one. This u star occurs because we assume Vn0 is a certain point u star. So we have this identity. And also in a similar fashion, we can manage to prove that in fact the absolute value of integration is this value. So that means psi n Vn is this value. So psi n Vn is integrable because this one is bounded, we have shown, and this one is also bounded. So this one is integrable, and furthermore it is bounded regardless of n. So we can, by Fato's lemma, we can see that this integral of psi of v, so you can take the pointwise limit here. So this integration is bounded, finite. I mean, this integration is finite. So that means psi v is integrable, right? Okay, so they're the same. So v has no tail. Why? Because assume v has a tail. Assume v has a tail. Then in this graph, psi of u or psi v looks like this. So if v has a tail, then it should be remained in the certain value here, around here. But around here, the value of psi v is strictly negative, to close to some value, right? So this should be integration of minus epsilon. That should be infinite. So it's not possible. So because psi v is integrable, v should have no tail. So that's the proof. And finally, let me just mention about the stability of this traveling wave. So that's my ongoing project. And also we can, in a similar fashion, I expect we can prove that a similar result to the classical result, a similar result to the classical one, which implies if initial data has a certain condition that is converges to this traveling wave. So this traveling wave is stable in that sense. That's it. Thank you.